Hello everyone, and welcome to our fourth lecture in abstract algebra. We're going to talk about congruences in this lecture, but before we do, I'm going to throw a few tidbits at you that are more closely related to what we did in lecture 3 than they are congruences. The first thing we're going to look at is this theorem. If G is a group with binary operator star, and A and B are elements in G, then the equations AX plus B and YA equal B have unique solutions. And the emphasis here is on the word unique. They have one and only one solution in the group G. So we'll let the hypothesis be given. Suppose that G is a group with binary operator star, and that A and B are elements in group G. And recall something that we just proved in lecture 3. If G is a group, then every element of G appears exactly once in every row of the group table. Okay, every element of G appears exactly once in each row of the table. So what? Well, let's apply this to what we're trying to prove. In the row headed by the element A, the element B appears exactly once. Yeah? Okay. So what? Well, let me draw a group table here. Here's my identity. And here's the column that B is going to appear in. Here's my identity. Here's the row headed by A. And somewhere in this row, the element B appears exactly once. Okay. We'll let X be the element that heads the column in which B appears. So here's X, and I was going to use red, but that doesn't show up too well. Here's our element X, the proposed solution to our equation. Oh, sorry about that. I just had to clear off some board space. Notice that B appears in the row headed by A, and in the column headed by X, our proposed solution. So what is this element B right here? This is in the row headed by A and the column headed by B. So this is A star B. I'm sorry. I left my brain at home this morning. A star X. So what have we shown? This implies that there exists an element in G such that an element X in G such that A star X equals B. And do we learn anything else from this? We do. The element B appears in the row headed by A, but it only appears once. And I'll say no. Since B appears only once in the row headed by B, headed by X, headed by A, excuse me. Since B appears only once in the row headed by A, there are no other solutions to the equation A star X equals B. And what's my reasoning on this? If there were another solution to this equation, then the element B would have to appear somewhere else in row A. For example, let's say we did have another solution. Then the element B would have to occur then the element B would also have to appear in row A and column Z but this would mean that B would appear twice in row A. And that's an impossibility if we have a group. Every element occurs exactly once. Now, I guess I'll just take the shortcut here. And say this. The equation y star A equals B has a unique solution in G. And if we were to do this out, we'd say, okay, look, the element B appears in the column headed by A exactly once. And whatever row B appears in, the element Y that heads that row is the solution. And since B only appears in column A once, there can only be one solution to this equation. So that's why I can say similarly, the equation y star A equals B has a unique solution in G. Here's another theorem that sort of goes with our previous lecture. If G is a group with binary operator star, and A and B are elements of G, then the inverse of A star B is B inverse star A inverse. So in other words, the inverse of a product, so to speak, is the product of the inverses in reverse order. The inverse of a product is the product of the inverses in reverse order. And let's prove this. We'll let the hypotheses be given. So G is a group with binary operator star, and A and B are elements of G. So that also means that since G is a group, the product of A and B is a member of G. The operation is closed on G. It's a group. And since this element A star B is an element of G, it must have an inverse. Every element in a group has an inverse. So we'll call it A star B inverse. But what is an inverse? What's the inverse of A star B? It's the element of G that we multiply A star B by in order to get the identity. So it's the element that we multiply A star B by from either direction in order to get the identity. And I might add, not only is it the element that we multiply A star B by, but it is the unique element that we multiply A star B by in order to get the identity E. And we've already shown that inverses are unique. So let's put this to the test. Okay, what do I do here? Well, I can consider this to be one element, because really it is. And I can choose to associate B with this element instead of associating B with the element A. So I can do this. Instead of associating B with A, I can associate B, whoops, let me remedy this. There we go. I can remedy this, or rather, instead of associating B with A, I can associate B with this element. So I'll have B star this element. And now I can choose to associate B inverse with B instead of with A inverse. Oh, but this is just the identity E. So we get A star E star A inverse. But the identity times anything is that thing. This is just A inverse. So we have A star A inverse, which is the identity. Okay, so if we multiply A star B from the right by this element, we get the identity. Does that also work if we multiply A star B from the left? Well, we'll check it out. We can consider this to be one element, and we can choose to associate A with this element rather than associating A with this element. That's what associativity tells us. So we have B inverse star A inverse star A and by associativity we can choose to associate A inverse with this element first. So we'll have B inverse star A inverse star A star B. But this guy, by the definition of inverse, this is going to be the identity element E. So we get B inverse star the identity star B. But B inverse star the identity, that's just B inverse. So we have B inverse star B, and that's the identity. Now, what's the point? Let's make sure we get it. B inverse star A inverse is such, okay, is the element that we multiply A star B by and I will add parenthetically from either side in order to get the identity. Hence, B inverse A inverse is the inverse of A star B. Okay, now on. Okay, congruences. We finally arrived. Let n greater than or equal to 2 be a natural number. So in other words, n is any natural number other than 1. The two integers a and b are congruent modulo n, and we denote it this way, exactly when the difference of a and b is equal to some integer k times n. So in other words, when the difference of a and b is a whole number multiple of n, then a and b are congruent modulo n. On the other hand, if a and b don't differ by a whole number multiple of n, then we say that a and b are incongruent modulo n, and we denote it this way. Now, before we do anything else, let's just look at a couple of examples, and then we'll give some more explanatory information. A equals 27, B equals 69. Okay, A minus B is 27 minus 69, which I hope is 42. And you know what? It would have been a good idea if I had selected an n here. And we'll say n equals 5, okay? So A is 27, B is 69, and n is 5. The difference of A and B is 42. And this is not equal to some integer k times 5 for any integer. In other words, A and B don't differ by a whole number multiple of 5. So A and B are incongruent. Modulo 5. And in terms of the numbers 27 and 69, 27 and 69 are incongruent modulo 5. Now, let's look at another example. And we'll have A equal 99, B equal 54, and we'll let n equal 5 again. So A minus B is 99 minus 54, and that is, what, 45? And that's equal to 9 times 5. So in this case, the difference of A and B is a whole number multiple of 5. And so A and B are congruent modulo 5. And in terms of the actual numbers, 99 is congruent to 54 modulo 5. And maybe we should do one or two more examples where n is something other than 5, just so that we don't become convinced that there's something magical and mystical about the number 5 in modulo arithmetic. There isn't. So let's look at a few more examples. A equals 163. B equals 219. And N equals 17. Okay. A minus B. Holy moly, what's that going to be? 37 plus 19 is 56. So negative 56. And let's see, 17 times 2 is 34. 17 times 3 is 51. Okay. So it is definitely not equal to any integer multiple of 17. This is not a whole number multiple of 17. So here, A is incongruent to B modulo 17. And in terms of the numbers themselves, 163 is incongruent to 219 modulo 17. And we'll do one more example. Okay, let's try this one out. Let's see if they are congruent mod 27 or not. A minus B is 276 minus 195. So let's see. 5 plus 76 is 81. They're both powers of 3, aren't they? Okay. Yeah, okay. So 81 equals 3 times 27. The difference of A and B is a whole number multiple of 27. Okay. So A is congruent to B mod 27. Or to state it in terms of the numbers themselves, 276 is congruent to 195 modulo 27. Excellent. Now let's get into a few more observations since we have a feel for what's going on here in modulo arithmetic. This is something that we know, but we probably don't know that we know it. It's called the division algorithm. And we're told, given a natural number n greater than or equal to 2, and an integer a, there exist unique integers q and r such that a is equal to q times n plus r. And this may look somewhat familiar now. We call r the remainder. We call n the divisor. We call q the quotient. And I guess that original number, I think that's what they call the dividend. But this is actually compatible with the way that we were taught to do division before we were really capable of grasping concepts. Notice that the remainder is never a negative number. And the remainder is also less than or equal to n minus 1. Now, n is the divisor. So this is saying that the remainder has to be less than the divisor. The remainder is non-negative, and it has to be less than the divisor. This is the way that we were always taught to do long division, although we weren't told about quotients and dividends and so forth and so on. And we weren't really told precisely the rules of what a remainder could or couldn't be. We were just prodded when we did something that was incorrect. They'd say, no, you can't do that, R's negative. We can't have a negative remainder. And think about it. When we had something like this, let's see. We'd be told 5 goes into 26 5 times with a remainder of 1. Now, we were never allowed to do something like this without correction. We would never be allowed to do this. They'd say, oh, no, you can't do that. 5 can go into 26 2 more times. Now, we weren't told that we couldn't have a remainder that's larger than the divisor or even equal to the divisor. And maybe I should touch on that point too. Suppose we have 25 divided by 5. We would never be allowed to do something like this. 25 divided by 5 is 4 times 5, remainder 5. They'd say, oh no, 5 can go into 25 one more time. Don't do that. It's 5 times 5 with a remainder of 0. Intuitively, we're familiar with the concept. We've just never had it explained to us precisely before. But the division algorithm essentially says that the quotient is the largest integer that we can multiply the divisor by and not exceed the dividend. So the quotient is the largest integer that we can have, where we can multiply the quotient by the divisor and not get something larger than the dividend, which means that the remainder is going to be non-negative and also less than the divisor. So let's take a look at this a little bit more. But we're not going to belabor this point too much. This is essentially correct division as we've been taught to do it since we were 7 years old. Let's see. So 19 times 7, I think. Let's see, 20 times 7 is 140. Yeah, okay. So 19 times 7 is 133 plus 3. Okay, 65 divided by 8. And you know, I think I'm writing this somewhat incorrectly. I think this is the way I really want to write it. 136 is equal to, okay, let's let n equal 7. Our divisor is 7. 136 is 19 times the divisor plus 3. And down here, our divisor is 8. And what did we have? 63, I think that's what it was. So 63 is 7 times 8 plus a remainder of 7. Now let's apply this to modulo arithmetic. Okay. We will now derive a very basic fact about congruences that we will continue to use from here on out. That we have the division algorithm, any integer a, and a divisor n greater than or equal to 2, where n is a natural number. The division algorithm says that a can be expressed this way. Some integer q times the divisor n plus a remainder r, where r is some integer between 0 and n minus 1 inclusive. But let's take this equation and rewrite it. Oh, I love that word. Yeah, we're going to rewrite this equation. A minus r is equal to qn. The difference between a and its remainder when divided by n is a whole number multiple of n. What do we know about two integers whose difference is a whole number multiple of n? They're congruent modulo n, right? So this implies that a is congruent to r modulo n. So given an integer a and a natural number n greater than or equal to 2, a is congruent to some remainder between 0 and n minus 1 inclusive. Congruent modulo n to its remainder when divided by n. we're going to define the set of remainders. So this set is the set of remainders modulo n. If we divide any integer by n, where n is a natural number greater than or equal to 2, the remainder has to be one of these numbers. And we call this the set of remainders modulo n.